All right, so for this first example, suppose we have a frequency response that looks like this. Okay. Now notice that this system can be written as 2 times h hat j omega, where h hat j omega is omega n square over j omega square plus 2 zeta omega n j omega plus omega n square with omega n equal to 100 and zeta equal to 1/2. Okay. So you can check if this is true, right? If you bring 2 outside, right, what you have remaining here is 10 to the power 4, which is the square of 100, right? And here I have j omega square. I have j omega times 2 times zeta, right? 2 times 1/2 is 1. Omega n is 100. So this is 100 j omega. And then we have omega n squared, which is again 10 to the power 4. Okay? So h of j omega is just 2 times of h hat of j omega, where h hat is in a typical form of the frequency response of a second order system. Okay? So with this, we can obtain the log magnitude of h of j omega as 20 log 10 2 plus 20 log 10 h hat j omega absolute. Okay? And this is the log magnitude of a second order system. So for a second order system, we know that it can be approximated by this 0 dB line when omega is much smaller than omega n, which is 100, and can be approximated by a 40 dB per decade line, right, which is minus 40 dB log 10 omega plus 80 for omega much greater than 100. Okay? So you can obtain that from this thing here. Right? So I have minus 40 log 10 omega plus 40 log 10 omega n. Omega n is 100. Right? Log 10 of 100 is 2. Right? 2 times 40 is 80. Okay? So this is what we get here. Okay? So 20 log 10 2 is 6 dB, right? So this is 6 plus 0 for omega that is small, 6 plus this when omega is large, okay? So you get something like this, right? You have 6, up to the break frequency of, omega n, and then decays by minus 40 dB per decade beyond that. Okay. So you can do the same thing for the phase. Okay. So a positive constant 2 does not change the phase, does not change the phase of this, h hat. So the phase of h is equal to the phase of h hat. Okay? And if you recall, this is 0 for omega less than 10. This is minus pi for omega greater than 1,000. And a straight line, minus pi over 2 log 10 omega over 100 plus 1 for omega within 10 and 1,000. Okay? And this is again obtained by applying this formula here. Okay? All right. So if you plot this out, it looks something like this. All right. So you have this straight line 0, straight line minus pi, and a linear line connecting the two. All right, and they intersect at the break frequency omega n. Okay, so this is the break frequency omega n. Similarly here. Okay. Right, so this is pretty simple, right? Because this is just a constant scale. This is just a constant scale of the original second order system. Okay. Now let's look at a more interesting case. Okay. So here we have a system with response that looks like this. Okay. Now, for this frequency response, we can actually write it as 1 over 10 times 1 over 1 plus j omega over 10, 1 over 1 plus j omega over 100, and 1 plus j omega. Okay. Right. So you can, sort of verify this by, multiplying them together. You'll see that this is indeed what we have on the top here. Okay. But the main point is that now the frequency response of this system can actually be viewed as cascading, three systems, one with frequency response this, the second with response this, and the third with response this. Okay? So we can actually view this as H1 j omega, H2 j omega, and H3 j omega. Okay? So both of these are exactly first order systems. Right. So both of these are exactly, first order systems, just with a different value of tau. Okay? All right. So this H1 has tau 1 with tau 1 equal to 1 over 10. with tau 2 equal to 1 over 100. And this is the reciprocal of a first order system. Right, this is reciprocal of first order with tau 3 equal to 1. Okay. So if you were to plot these systems out separately, what would they look like? Okay. All right, so suppose this is 0.1, 1, 10, 100, 1,000. Sorry, 1, 10, 100, 1,000. Okay? And this is 0, minus 20, minus 40, and so on. Okay. Now, if you look at this H1, right, this is a first order system, right, with break frequency at 1 over 10, which is 0. I'm sorry, break frequency is 1 over tau 1, which is 10. Okay? So you have a break frequency here. Now, for a first order system, it's approximately 0 before the break frequency, and then decays by 20 dB per decade, right? So it decays by 20 dB per decade. Okay? So this is H1. Let's say (20 log 10 of H1). Okay? And then what is H2? Okay. So what is H2? H2 is also a first order with a break frequency at 100. Okay? So H2 is 0 dB up to the break frequency, which is 100. And then after that, you start to break at 20 dB. Okay? Sorry. I want to draw this with the same scale. So let's see if this is the same scale. Okay. Should be approximately. Okay. Or maybe I can move this up a little bit. Okay, something like that. Okay? Okay. So the slope here is minus 20, and the same here. Okay. Now, what about the third term here? The third term has a break frequency at 1, but it's the reciprocal of the first order. Okay? When you have a reciprocal, okay. When you have a reciprocal, it's basically minus the log magnitude of the original first order system. Okay. So if, the original first order system would have a 0 up to frequency 1 and start to decay by 20 dB. Okay. But minus that means that you would have 0 up to 1, right? 0 dB up to 1. But then you will start to increase by 20 dB per decade. So you'll start to increase by 20 dB per decade. Okay? So you basically add all these three together. Okay? So your 20 log 10 of the magnitude of h is equal to 20 log 10 of 1 over 10, which is minus 20, plus 20 log 10 of the magnitude of h1, plus 20 log 10 of the magnitude of h2, minus 20 log 10 of the magnitude of 1 over h3. Okay? So suppose you add all these three together with a minus 20 dB. So you start out with 0 plus 0 plus 0 minus 20. So you start out with minus 20 dB here, okay? And once you reach frequency 1, you start to increase by 20 dB, okay? So you start to increase by 20 dB. So you will go from minus 20 to 0 in 1 decade, okay? Go from minus 20 dB to 0 in 1 decade. Okay. But once you reach omega equal to 10, right, you have this force going up by 20 and this slope going down by 20, which cancels out. Okay? So at this point, the upward trend cancels out with the downward trend, so it stays flat here. Okay? But then once you reach 100, you have two slopes going down and one slope going up. Right? Suppose that these two cancel out, you still have a 20 dB slope going down. Right? So you have a 20 dB slope going down means that you will start from 0 and decay to minus 20 dB after 1 decade. Right? So this point is minus 20. Okay? Right. So this is an example to show you that this asymptotic approximation of the behavior of these frequency responses is very convenient, because even though if you have a more complex system, you can still split them, right, treat them as a cascade of these first and second order systems, which have these very simple behaviors that you can just aggregate together to get a simple trend of this more complex system. Okay? And this is done without really computing the exact value of h at every specific value of omega. Okay? All right. So you can also do that, for the phase as well, but I'm going to leave that for you. Okay? Okay. All right, so this is studying the time and frequency characteristics of these first and second order systems, using them as basic building blocks for more complex systems of this type. Okay. So we can do something similar for discrete time as well, but in discrete time, we don't have such a Bode plot, right? Because in discrete time, the frequency is only between a 2 pi range, right? So we wouldn't be plotting something that is in log scale of omega, right? So we don't have, such a asymptotic study for the discrete time case, but you can still, observe certain trade-offs between the time and frequency domain. Okay, so I'll just quickly go through this because this is not much different from what we already discussed. So suppose we also start out with the first order system, which in discrete time is written as this difference equation. By taking Fourier transform on both sides, you get this frequency response here. Okay. So a frequency response of this type, you know immediately what is the impulse response, right? The inverse Fourier transform. And summing or accumulating this impulse response gives you the step response. Okay? All right, so here, similar to the time constant that we had before, here the response time of the system is determined by the value of this A here. Okay? So if you have an A value that is small, okay? If you have an A value that is small, then your response will actually decay pretty fast. But if you have an A value that is closer to 1, right, that is larger, closer to 1, then you have a time domain response that decays slower. Okay? Now, what's different from the continuous time case is that, for first order systems in the continuous time case, you always have these, monotonically decaying exponentials. Okay, you do not have oscillating behavior in first order systems. But in discrete time, you actually may have this oscillating behavior if your factor A is less than 0. Okay, because if this is less than 0, then you will oscillate between plus and minus values depending on whether this exponent is even or odd. Okay, so you observe this oscillatory behavior, or what we call ringing, when A is less than 0. And you can see that in these cases here. Okay, so for example, for A equal to 3 minus 3 over 4, you see this thing that oscillates between positive and negative values, but still decaying towards 0. Okay. All right, so this is the impulse response. If you accumulate the values, right, pass this through an accumulator, then you get the step response like this. Right? So if A is positive, then smaller values of A will give you a step response that rises faster to the desired gain, okay? But if A is larger, then it takes some time to reach this desired gain, okay? And furthermore, if A is negative, then you may observe this, this oscillatory behavior before it settles down to the steady state value. Okay. All right. And you can also look at its frequency response. So we already did this before in previous chapters. So if you look at the magnitude and phase, which we observe, in terms of the linear, scale of the frequency instead of the log scale, because omega is always between a 2 pi range, right? Then we observe behaviors as shown in these plots here. Okay, so first of all, suppose that A is greater than 0. If A is greater than 0, then as omega increases from 0 to pi, right, cosine omega becomes smaller and smaller, right, because cosine 0 is 1, right? As it goes towards pi, it goes towards -1. So as this decreases, this denominator increases, and the whole thing decreases. So for a greater than 1, you can see that the log magnitude has a peak at 0 frequency and then decays towards pi and minus pi. Okay? So this is for a greater than 0, which attenuates at high frequency. Okay. Now, if you want a filter, right, if you want a system that lets through signals that, have a narrower, lets through, a less amount of signals, right? Meaning that you should have a narrower frequency band, then you would have to have a larger value of A, okay? So a larger value of A allows you to have a narrower frequency band, being more selective in the signals that you let through. But then this means that in the time domain, you would have a slower response, okay? So you have sharper for A closer to 1, but slower time response. Okay? So this is a trade-off that is somewhat similar to what you see in continuous time. Okay? Now when A is less than 0, right, when A is less than 0, then the behavior is opposite. Right? In this case, as omega increases towards pi, this denominator actually becomes smaller and the whole thing becomes bigger. So in that case, you actually peak out at high frequency instead of at low frequency. Okay. Okay. Right, so this is all I want to cover for this chapter. So this chapter is mainly just, sort of reviewing what we, discussed in previous chapters, right? How to utilize this Fourier transform to help us analyze or study the trade-off between, time and frequency. Okay. So the only thing new I would say in this chapter is, how to plot out this Bode plot, right, for continuous time spectrum, and how to use this asymptotic lines to help you study the approximate behaviors rather than having to, compute the specific values of the response at each frequency point. Okay? But, for all the other things, we already did several times in previous chapters, such as, deriving these transforms. Okay. All right, so I have a couple more minutes, so let me just start with the next chapter a little bit. Okay. So if you want to know more about, where you would encounter such second order systems in practice, there are a couple of examples in 6.7. Okay, so see chapter 6.7 for some examples. Okay. All right, so this would occur in typically, RC circuits or RLC circuits for second order systems, or these, mechanical systems that we just showed. Right. So for example, the braking system or this, shock absorbing system of vehicles, right? These mechanical systems are all examples of second order systems. Okay. So I want to talk a little bit about the next chapter, which is on sampling. Okay. All right, so somehow my files, I have a clean file that's not synced to my computer. Okay. So maybe I can use this old file for now. Okay. So in this chapter, we want to talk about sampling. Okay. So again, like I said, the core of this class we have taught in chapters 3, 4, and 5. Okay, and then in the remaining chapters, like in chapter 6, right, we see how to apply this to study time and frequency. And then in chapter 7, we try to use this to study, the relationship between continuous and discrete time. Okay, and we'll talk a little bit about chapters 8 and 9, where we have this Z transform that is an extension of this Fourier transform. Okay, for systems that do not have finite energy. Okay, so for those part, we would not cover fully. But just to give an idea of how it can be extended to those cases. Okay, so in chapter 7, we talk about sampling. So what is sampling? Sampling is the process of converting continuous time signals to discrete time signals. Okay? So for example, suppose that you have a continuous time signal like this. Okay? Now, we often would like to, right, instead of dealing with this continuous time signal, we often would like to take samples from this signal as a representative of this continuous time signal. Okay? And what I mean by sample is taking the values of this continuous time signal at discrete instants in time, okay? Usually at equally spaced instants in time. Okay? Now, if we can use these discrete samples to represent the continuous time signals, then we can process, whatever we want to process in discrete time rather than in continuous time. And the reason for that is because, modern technology treats digital processing much more efficiently than analog processing. Okay, so if we can convert these analog or continuous time signals to, discrete time and maybe even digitize it, we can often use efficient digital circuits to deal with them, okay? But then the question is, when can we use these discrete time samples to uniquely represent a continuous time signal, okay? So suppose you take these discrete values, this given set of discrete values. From this figure here, you can see that there are actually infinite continuous time signals that have samples corresponding to these values, right? The signal could be something like this, or it could be something like this, or anything that intersects with these points, okay? So when is it possible to use these discrete samples to uniquely represent the continuous time signal? Okay. So intuitively, right, if you compare between these curves here, right, intuitively, in order to, have these points well approximate the continuous time curve, it means that the curve should not change rapidly relative to the sampling time that we're using, okay? So the intuition is that the continuous time signal should not vary rapidly from sample to sample, right? So that we can well interpolate it back into the original signal, okay? So the signal cannot vary too fast. Or in other words, this is saying that the signal should be band limited, right? It should have frequency components that are low enough, right? So that it does not vary too fast, okay? And we will derive this more rigorously tomorrow, right? So let me stop here.